So this session is this lecture is a short introduction to the basic ideas of Monte Carlo methods. So the kind of plan is I'm just going to give a very brief introduction to the basic idea of Monte Carlo methods and some of their applications. Then we're going to focus on looking at Monte Carlo techniques for integration. Monte Carlo techniques are particularly good for integrations of multi-dimensional integrals. Then we go through a bit of theory. We're going to talk a little bit about simulation of models, and then end with a bit of simulation of gambling. So what is the Monte Carlo method? I mean, at the very basic, it's the use of random variables to solve mathematics problems, sometimes known as simulation. So Monte Carlo methods have a very broad application, and they can be used to solve problems with no analytical solution. This analytic solution means if you can actually solve the equations, you can solve ordinary differential equations or various things. The Monte Carlo method is usually has a wider applicability, and it can be a simpler method than a complicated analytical solution. Originally, although they have a slight history, the start of Monte Carlo methods were developed during the Second World War, and they were developed as part of building nuclear weapons, and at Los Alamos and places like that. And the reason they started to be used is because they also require computers to be used. And so it was no surprise that Monte Carlo methods started out just as the first computers were developed. And it's called Monte Carlo for like the gambling at Monte Carlo on the continent. So I say we're going to focus mostly on Monte Carlo methods to integration, but it's used a lot to solve physical systems such as modeling of magnets or problems in quantum mechanics. It can also be used to do, perhaps surprisingly, if you want to do here this trace of an inverse matrix, which I certainly need in my research. And it's more efficient to use Monte Carlo methods to use some random noise, particularly when the order of the matrix reaches like 10 million. You can't use sort of normal techniques. You have to use some kind of randomness. Okay, so the application we're going to look for Monte Carlo methods are the first application is just doing multi-dimensional integrals. And I have a couple of slides just on the modification of multi-dimensional integrals. They're used in many areas of finance, particle physics, statistical physics. For example, the moment of inertia of a continuous body, you sum over here is the density, so you sum over x, y, and z in 3 dimensions, weighted with r squared, and this tells you how a body, the dynamics of it when you spin it around, when it rotates. And to find out this a moment of inertia, you have to compute this 3-dimensional integral. And v is the volume. So that's one application for, why you need to do integrals in more than one dimension. In particle physics, these diagrams down the bottom are called Feynman diagrams, and you may have seen these little things. This little squiggly line is a photon. This curved line here is an electron. So people draw pictures of these things, but when you actually get to calculate them, these things are actually, on paper, are actually 8-dimensional integrals. And there's, well, it doesn't really matter what that is. And sometimes people need 12-dimensional integrals, 16-dimensional integrals. So part of computing these things is actually have to be able to compute multi-dimensional integrals. So you need an efficient method to do that. Perhaps for you, the most important area you'll see multi-dimensional integrals is in Bayes' theorem, which I've written here, which is a relation between conditional probability. So this is the basic Bayes' theorem, conditional probability of A given the event B, which you can compute from these factors here. When you do continuous variables, if you have property of conditional probability of Z depending on X, conditional probability of Y depending on X, then the probability of the event Y given X, Y, and Z, turns out you need to compute a 3-dimensional integral. And in Bayesian statistics, you need to compute much higher dimensional integrals, and you'll see that, and these are the areas where some kind of randomness or some kind of Monte Carlo method needs to be used. Okay, and one of the really big multidimensional integrals are in finance. So I've taken a quote. So the quote I'm just going to read out. Central goal of mathematical finance is the pricing of financial products known as derivatives. As it turns out, prices of such products can often be represented as suspected values, given as integrals in high dimensional, sometimes infinite dimensional spaces. Typically, the price of a derivative depends on quantities, stock prices, interest rates, etc. And in specifically, so being able to compute multidimensional integrals as part of mathematical finance. And here's an example I found from a paper in 1992, when the variables are this is an example from claritated mortgage obligation, some part of finance, and they require to compute multidimensional integrals of dimensions up to 360. So, you've done in the past one-dimensional integrals, you've been introduced to multidimensional integrals, and there's a great need to be able to compute them efficiently on the computer. In Python, the SciPy library is the one with all the sort of has a lot of the typical kind of scientific routines, and they have routines to do quadrature, and the routines, so they usually have quad, which will do integrals in 1 dimension, double quad, which will do integrals in 2 dimension, TP quad, which will do integrals in 3 dimensions, and then there's a generic n quad. And we'll see that, and then many applications need high dimensional integrals to be computed, and one way of efficiently doing that is to use Monte Carlo methods. Okay, so that's the word example. So it's important to be able to compute these things efficiently. So what's the basic idea? So if here we're just computing an integral alpha, we're going to integrate the function fx. I'm not going to specify here between 1 and 0. So we're trying to compute the value of alpha. We've got an integrand, and it could be we can't do it either by hand or using Maple. We can actually, using the ideas of probability functions, we can actually rewrite alpha as the expectation value of the function u f on random numbers from the uniform distribution. This means the numbers are just random, evenly distributed between 0 and 1. So if we can generate random numbers between 0 and 1, we can have an estimate of the integral by taking the average. So ui, the random numbers between 0 and 1, you apply the function to them and then take the mean, and that gives you an estimate of the integral. So we'll see later when we do the code, actually what we're going to do. We're going to generate a sequence of random numbers, ui, and then we're going to average them, and that'll give us an estimate of the integral. And this is related to the law of strong numbers, that as this sum goes to infinity, this summation approaches this integral. This is law of large numbers. So you've seen this normally in the past. You'll have a probability distribution, and you're trying to estimate whether sample numbers come from the probability distribution. In this case, we're rewriting an integral in terms of probability distribution. Then if we write the numbers as random numbers coming between 0 and 1, we can kind of compute this thing here. Okay, because we know that, so we're using some kind of randomness, so we'd like to have some kind of error or confidence interval on the result. So you can compute this by computing the variance. So recall in the previous slide, we're trying to compute the integrand of fx between 1 and 0. We want to know what the sort of error is on the process. So in principle, you can compute the variance, which is the integration of fx minus alpha, and alpha is the sort of mean value squared. But the trouble, I mean, if you can't do the original integral, you can't do this integral either. It turns out you can actually estimate an error by looking at the standard deviation. So you can compute the standard deviation by taking the, so use this formula here. Essentially, you take the square of the deviation of random numbers from the mean, square that up, And then there's this funny, instead of averaging over n, there's a long statistical story, you average by 1 over n minus 1. And this gives you the standard deviation. So essentially you're looking at the integral, you're computing an estimate of the variance, divided by roughly by the square root of n, the number of samples. And as the number of samples gets bigger, then the error is reduced. So this is the key question. So to compute the error, as you have more samples, the variance stays roughly the same, and as the number of sample goes up, the error goes down like the square root of 1 over n, which is the sum of numbers. Okay, and just to say, well, we'll see an application later, but this is why the method is computable, because as you know from integration, it can be quite tricky to do the integration. With the Monte Carlo method, essentially you just, you know what the integrand is, so you can easily apply random number. You can have the integrand, you can apply the random numbers here, sum them up. So all this is very doable, there's no tricks or anything, it's a well-defined procedure. And then you can compute the error as well using this formula, using the standard deviation. So this is why the Monte Carlo method is good, because if the integrand is very complicated and you can't do the integral, then the Monte Carlo method gives you a procedure to compute the answer. Okay, so the Monte Carlo method works for integration, and if you remember in first year, you looked at various ways of computing, doing integration numerically. So down here, if you want to do the integral between 1 and 0, compute this numerically of the function fx dx, there's a rule called the trapezoid rule, which is like this. Essentially, you take the function at various points and average over them, and this will give you an estimate of the integral. And there are many other different rules. In the first year, you also saw something called the Simpson's rule. So in one dimension, these methods are fantastic, so you don't really need Monte Carlo integration. So what you saw in the first year is you just had a one-dimensional integral, and you use a rule like this, sum over the function at some points. And these methods will generalize if you'd have to do like a two-dimensional integral or three-dimensional integral. You just need a lot more points. Unfortunately, when you do the theory, you find the error on the integration for the trapezoidal rule goes like order. This is how expensive it is. This means the number of function evaluations, or how long the program's going to go. And it depends on 1 over the number of points, 2 divided by d, where d is the number of dimensions. So if you look at a multi-dimensional integral with dimension d, where d could be 2 for 2 dimensions, or 3 for 3 dimensions, the actual error depends on the number of dimensions. And this means as the number of dimensions goes up, the error goes down. So we saw on the last slide, if you're doing multi-dimensional integrals with the Monte Carlo method, the errors go like 1 over n to the half, where n is the number of samples. It's the number of times you apply the functions. And you can see that the advantage of this is going down slowly as the number of samples, the square root of the number of samples, but it doesn't depend on the dimensions. And so the error on the Monte Carlo integration is independent of the dimension of the space. So these methods here, so the kind of methods you've seen to do numerically to do integrals in one dimension, you'd always use those. You'd always use Simpson's or trapezoid rule for one-dimensional integrals. They're completely fine. Monte Carlo method's not great, but if you want to do multi-dimensional integrals, as which we sometimes do for many applications, if you're doing statistics, Bayesian statistics, you need to do calculations of multi-dimensional integrals. And in that case, you need to do a grid of points, and you'll find the error goes very slow once you go beyond 3 dimensions. But the Monte Carlo integration is independent of the dimensions. So sometimes we'll just to explain the method, we use Monte Carlo methods for one-dimensional integrals, but really their main use is actually in multi-dimensional integrals, where they're much more efficient than a sort of trapezoid rule or Simpson's rules, because it's just less work. Okay, and this is This is named, this depend on the fact the error depends on the number of dimensions. It's called the curse of dimensionality. This means as you start doing large multi-dimensional integrals, your calculations get a lot slower if you're not using Monte Carlo methods. Okay, so here's an example computing the integral of cos to the fourth power between 1 and 0. So actually I have an example on the DLE which you can use as a basis for if required. So let's just go down to Spider. Okay, so this is the one-dimensional integral. So if we look at the problem here, we're going to do the integral of between 1 and 0 of cos x to the fourth power. So we're going to use Python, and we're going to first, as I say, for one-dimensional integrals, it doesn't make so much sense to use Monte Carlo methods, but this is a good way to sort of test out our understanding. So here we have an integrand who wants to do cos to the fourth power, and here's how I code it up. The SciPy library has all a lot of libraries to do like scientific and mathematical programming, such as quadrature. So this is why we have to import a quad, which will do it. So we have to define the integrand, which is math.cos x to the power 4, because remember that's what we're trying to compute. And so here's just using the SciPy library. Then I want to do the Monte Carlo method. What I said was to do this the actual method here is we're going to do, so we're trying to compute this integral. This time it's cos x to the power 4. So we're going to pull random numbers between 0 and 1, apply the function to it, apply the integrand to it, and then take the mean. And this is what this code is doing. So we have 1024 samples. I'm going to store where x is. So here I'm looping over between 0 and n sample minus 1. This Rx equals np to random creates a random number. And then I'm going to store xi equals the integrand, and I'm applying the random number to it, and I'm storing it in the vector xi. Then at the end we're going to take the mean, and then we're going to take the error. So we take this STD as the standard deviation, and then to get the error, the confidence interval, we take the square root of the number of samples. Okay. Okay, so let's run that. Okay, so this first integral here is using the Python quad function, and that produces 0.94681 with an error, a very small error. These methods this routine here, quad, is very efficient for one-dimensional integrals. With 1024 integrals, however, the Monte Carlo method gets 9456 with an error of 3.26 times 10 to the minus 3. And it's within statistical errors, this number agrees with that. It's obviously a lot less, not as accurate. If you want to make it more accurate, we can just increase the number of samples in the Monte Carlo method. So if you run it again, so now we've got essentially 10,000 samples, and what's happened here is there's some randomness to the errors, so the actual number is sort of the same. But here before, with just 1024, we had an error of 3.26 times 10 to the minus 3. When we multiply the number of samples by 10, then the error goes down a little bit to 1 times 10 to the minus 3. And that's the fact that the error goes like I want to mention the error goes like the standard deviation divided the variance divided by the square root of n. yeah, so to make it more accurately, so here we apply the random numbers to the integrand. So the integrand was up here at the top, just cos x4. We loop over the Monte Carlo samples, store the applying the integrand, putting the random numbers into the function. Then we take the mean. Then we compute the standard deviation, and then we have to compute this square root here on the number of samples, and that gives us the error and the central value. And then to increase the to decrease the error, we have to increase the number of samples. So in this case, we've got a number, but it's a bit it's not particularly accurate in one dimensions. Okay, so what do we do for 2 dimensions? So, I mean, this is just a little test case. Here's the test case of the integral between 1 and 0, 3x squared plus 5y squared, integrated to dx dy. So we're going to use the Monte Carlo method. So we have the function here, returning 3x squared plus 5y squared. We're starting off with 1024 samples. This x, we're creating a storage area with n sample 1024 numbers to store it. And now now our function depends on x and y. So we loop over the number of Monte Carlo samples, 0 to n sample. We generate 2 random numbers, one for x and one for y. And then we apply the function, and then we store it in this vector x. And then to compute the estimate of the integral, we take the mean, and then the error is the standard deviation divided by the square root. So this is like the error on the mean. So this gives us the Monte Carlo estimate, and then we get an error. So so this is similar to the one-dimensional case, and so even though these integrals are more complicated, the procedure is the same. You generate random numbers, use them in the integrand, repeat this n sample times, and then take the mean. So, I mean, even though this is a very simple multidimensional integral, but as the multidimensional integrals get very complicated, this procedure is always a way of getting a good estimate. Okay. Okay, so here's the code. It's slightly different to what I have in the slides. So we're trying to integrate 3x squared plus 5y squared between 1 and 0. Here I've done something, I've used a routine, this double quad, which will do a 2-dimensional integral. We'll see that's more efficient. And then here is the code to do the multi-dimensional integral using the Monte Carlo method. So we loop over the number of samples, 0 to n sample. This is 0 to I ranges from 0 to n sample minus 1. We generate a random number, another random number. Then we apply that to the function, the x and y. And then at the end of it, xi contains the functions for each of the 2 random numbers. Then we take the mean, and then we compute the error. It's like a statistical thing. Take the standard deviation, and then divide by the square root of the number of samples. And also this routine, I'll have some timings in as well. Because what I do is, up here I call, this tells me what the starting time is, and at the end of the routine I work out the time minus the time at the start, and this tells me how many seconds. Run. Okay, so now even the 2-dimensional integrals, this double quad has worked very well. And then my Monte Carlo estimate is the mean value here with the standard deviation divided by the square root of the number of samples. And it's taken sort of a very few seconds. if I want to get the error more accurate, if I want to reduce the error, I can increase the number of samples. Then let's run it again. Okay, so what I've done here is I increased the number of samples by a factor of 10. So for the Monte Carlo estimate, the error has gone down. It used to be 5.35 times 10 to the minus 2. The error is now 1.72 times 10 to the minus 2. So the error has gone down because I got more Monte Carlo estimates. So my error has gone down. But then you can kind of see the slight problem, whereas before it's taking sort of 5.9 times 10 to the minus 3 seconds, because I've increased the number of the Monte Carlo samples, the time taken has gone to 1.55 times 10 to the minus 2 seconds. So, I mean, that's the problem with the Monte Carlo method. It'll give you a very imprecise number very quickly, but if you want to get the number more precisely, you have to use more Monte Carlo samples, and that can take a longer time. Okay, so the sort of good news about the Monte Carlo is it's easy to code up. So if you want to do a multi-dimensional integral, there's a well-defined procedure. There's no kind of tricks in it. But the main problem with it is the method's slow. And this comes down really to what the error is. And then the error goes like some constant divided by the square root of the number of Monte Carlo samples. And actually, you know, the cost of the calculation is proportional to the number of Monte Carlo samples, and the error goes down like the square root of the number of Monte Carlo samples. So here I've done an integral, just for example, I've done an integral from 1 and 0 cos 50x plus sine 20x squared between 1 and 0, and I get 0.973 plus minus 0.032. So I've only really got two significant figures. If I want to get a much smaller error, say 10 to the minus 5, the way to reduce this error is the other thing is to use more samples. And then you can use this formula here if you solve. I know what the error here is. Oops. I know what this error here is, 0.032. And I know the number of Monte Carlo samples, so I can solve for A. And then once I have A, I can estimate how many samples I need to get a given error. And what I claim from this example, I need around 1 times 10 to the 10 samples to get an error of 10 to the minus 5. And that also means, you know, how long the calculation takes is proportional to the number of samples. So we're going to need, you know, a lot more samples to get the thing very. We need a lot more samples to get the number very accurate. And the thing about Monte Carlo, whenever you do it, because you should always quote an error with the results, because otherwise you don't know how many digits are correct. So you should always compute an error when you compute an integral using Monte Carlo techniques. Okay, so when you find out in practice, the error goes like 1 over the square root of the number of samples. And you know, sometimes you need, to get accurate results, you need a lot of samples, and this can be very, very slow. So there are a number of ways to reduce the number of samples required, and these are called variance reduction methods. And the basic idea is to reduce the value of A. So you you do clever things with the integrand and mess around, and you can sometimes reduce A. So one of the techniques we're not really going to talk about is importance sampling, and that means you have to do a clever choice of probability distribution. There's something called stratified sampling. This is, instead of doing the integral between 1 and 0, it can be more efficient to do the integral between 1.5 and then 0.5, and that essentially breaks up the integration region, and you can actually sometimes get the errors down using that. And also, the people who do, I said one of the applications that that uses multidimensional integrals is Bayesian statistics. Sometimes they have very high dimensional integrals. So there are techniques called Markov chain Monte Carlo, which are not discussed in this module, but they are also very clever ways of reducing this A and getting a smaller error for a given amount of computational time. So, I mean, what I said before, Monte Carlo methods really come into their own when you do large multi-dimensional integrals, like 5 dimensions, 10 dimensions. They're much better than using generalizations of Simpson's rule and trapezoid rule. But sometimes we'll look at one-dimensional integrals using Monte Carlo just to test some of the methods. But the main thrust of the main use of Monte Carlo is some large multi-dimensional integrals. So we're just looking at 1D integrals to have a play with the formalism, essentially. Okay, so I said here the error goes like A divided by n sample. There are actually things called quasi-random numbers that are a bit less random, and those things actually have an error like B divided by n sample. So the error goes down a bit quicker. This is I mean, that's fine. So these things are not as random as proper random numbers, and unfortunately this is a sort of an approximation. So for very large dimensional integrals, this technique doesn't work, but it works for sort of largest dimensional integrals. And the fact that the error is going down like 1 over n sample rather than the square root of n sample means these techniques are more efficient. Well, efficient, well, I say that it's a lot easier to reduce the errors using quasi-random numbers. Okay, so far we looked at integration. We've just looked at so our original formulation, we're looking at functions, and we've used uniform random numbers to compute this integral. But by sort of analogy with statistics, you can break an integrand up into fx and hx, where hx is the probability distribution, and a distribution can be used. And then you generate, to do this, you're actually generating random numbers from the h probability distribution and then applying them to the function. So this is like the expectation value of the function f. And for this to work, you have the xi random numbers distributed according to the hx probability distribution. And there's some, so you've broken up the integrand into a probability distribution and something to measure, which is the fx. Okay, so the above, there are some issues with normalization. The above formula at the moment assumes that if you integrate hx between infinity and minus infinity, you should get 1. If it doesn't have the correct normalization, if somehow you, when you integrate from minus infinity to infinity hx dx, you get some number which is v, then you have to modify the formula just to get the normalization right. So then the integration of fx times hx between minus infinity and infinity is v, and then the mean of fxi. So these xi are now drawn from the hx probability distribution. Okay, so and this is one of these tricks that this trick is also known as kind of importance sampling, which we're not going to talk about much further in this session. Okay, and just because I'm a physicist, in statistical physics, if you want to, so the way we understand some physical systems in statistics, in physics, so the expression for, say you want to know the magnetization of a magnet, you have a system, there's a procedure for computing that where you integrate over all the degrees of freedom with this weight function here, which is the energy, ER, beta is 1 over the temperature, and then you integrate over all degrees of freedom, So this is actually an expectation value. So the magnetization is an expectation value, and this 1 over z is a normalization factor to make sure that this integrand, when you integrate it without a, it gives you 1. So a is the function to be measured, and it could be something like the magnetization. If you have a whole bunch of magnetic spins, they're all bogging up. Beta is 1 over the K is a constant, T is the temperature. So this is the way if you look at a physical system and you want to know what happens if you change the temperature, then under appropriate conditions you have to compute this large multi-dimensional integrand. So there's a huge community of people using Monte Carlo techniques, and this expression here is actually a large multi-dimensional integral. Okay, just to give a flavour of these ideas, I want to just show you a much simpler example, which doesn't require so much background. I should point out that some of the physics techniques used here to compute these integrals are now commonly used in statistics. So some of the algorithms written to compute these in physics are now being used in Bayesian statistics. So some of you, if you take some modules in 3rd year, will meet something called STAN, which does kind of Bayesian statistics. And the original motivation for STAN, which is a library used to do multidimensional integrals in Bayesian statistics, came from a physics-based system like this. Okay, so the simple example we're going to look at is something called percolation theory. This is just to give you some idea of how simulation can be applied to a physics model. So what happens is you have a grid square. So this is a little model, and what you do, you loop through each site. At each site, you generate a random number. If the random number is less than the fill probability, this p rho, then the site gets filled. So what happens is you can kind of repeat this process and loop through the lattice, and you get some points. So here, if the random number generated is less than this rho p, you put a point. If it's and then here the random number is bigger than rho p, then you get nothing, and you get a little pattern. So if the probability is low here, you get a very sparse pattern. If the probability is very big, this p rho, it's very large, then you get many points crossing. So this is an example of a sort of physics-based system, that a very stripped down thing. So what people are interested in is something called spanning paths. So you have this random systems, and when you look at it, a spanning path is can I start from this side of the lattice, and can I just hop from the points? So in this example here, I can hop from here to here to here to here, up here, up here. So I can actually step from this side of the lattice to the other side. And so this is a part of a simulation with a large probability. So remember, what happens is you go through the sites, and there's a sort of filling probability. If the random number is smaller than p, you fill it. So here, if the probability is low, if I can only hop from black dot to black dot, and here I start here, but I can't get to the other side by traveling over the dots. In this example, there's a higher probability. Here I can start from here, go up here, here, down here, and here. So with this system, I can actually cross the grid, and this is all like the Monte Carlo method. It's all based on probability. So what we're interested in is spanning paths. Can you get from one side by hopping on the live things? And for certain, so this is all controlled by this number here. There's rho p. So this number is between 0 and 1. So for very small numbers, you can't span. For very big numbers, you can span. Get close to 1. Then there is some level. There's a number where there'll certainly be spanning paths, and some of the issues depend on how big the square is. Okay, so why is this thing interesting at all? So people use it for models of these things. So one of the things that can be modeled is the spread of forest fires. the spread of terrorism. So this is like people communicating each other via, on hidden Facebook groups, and also the spread of infectious diseases. Uh, so like a forest fire, this one thing would be one tree burning, another tree burning, and then the issue is if the probability of trees burning gets enough, then it can kind of spread through the entire forest and burn everything down. So that's why this sort of application of these spanning trees. But for low probabilities, so this side here, if this thing goes on, there's a low probability, but there's no way to connect both sides of the grid. And obviously, it's also a way of modeling infectious diseases. Okay, and this is a very simple model of, say, the spread of a forest fire or the spread of infectious disease. So if there's, but there are kind of arguments to say that these simple models are sort of easy to understand, but there are arguments to say that why they're useful for more sophisticated systems. Okay, so here I just have a paper where somebody's actually using these simple ideas of percolation type models, where you have a certain probability of one of these sites being filled or not filled, and somebody's used that as a model of trying to understand the spread of COVID. Okay, and there are many other ways to fit COVID data. SRR models. So this is just one particular way of understanding the models, trying to understand the spread of COVID, say. Okay, so the final application I want to talk about with Monte Carlo methods is to study simple gambling problems. So some of the problems we're going to look at, so we can just look at one example, and some of these problems can be solved analytically using theory, but the Monte Carlo way is a simple way to study the problem. So we're going to simulate a sort of online gambling game. You have two players, A and B, and they start with stakes of £10 and £20. And the game is you select a random number R. If R is less than 0.5, A wins. Then A gets £1 from B. If R, the random number, is greater than 0.5, B wins. Then B gets the pound from A. And the game is terminated when either A or B runs out of money. So this shows the use of a kind of random number to simulate a game. So in here we're just talking about one game. So you have a random number. So this is like a sort of computer simulation of a roulette wheel. Instead of that, we just use a random number, a random number on the computer. And so this will be one game. And then you can kind of repeat this. You can repeat this like 1,000 games. And then you can get some idea of the probability of A winning or B winning using this strategy. Okay, so here's the Python code for simulation of a simple game, and the code's on the DLE, which is the code gamble_game.py. So here's what we said: A has £10, B has £20, and here's a game. So we continue the game while A has money and B has money. So here's the game. We have a random number. If R is less than 0.5, then A wins. So A stakes increase by 1 and B stakes less than 1. Or if the random number is greater than 0.5, then B wins. So B gets £1 and A loses £1. And then we keep doing this. This is a while loop. Keeps going while A stake, the amount of money that A has, the amount of money that B has, is greater than 0. And then you can also have a count. So you just count the length of the game. Okay, so if I repeat this, So this is one game, but I can put an outer loop in here and do a loop over like 1,000 games, and then I can kind of count the number of times that A wins or the number of times that B wins. So that's what the results here show. So we have initial stake of A is £10, B has £20. If I repeat this 1,000 times, and then with the Monte Carlo process, because I've repeated the thing 1,000 times, I know that the mean length of game is 200. And then I repeat it 1,000 times. I can just count the number of times A wins and the number of times that B wins. So it actually, B wins 0.643 and A wins 0.357. So B has an advantage because they just start with more money, so they just win more. But by using this Monte Carlo, you can analyze this simple game to tell you who'll win. You can also then, so at the moment this is a very kind of simple betting strategy. That every time you bet a pound, depending on the random number, but you can try investigating different betting strategies. So there's the martingale strategy where a gamble doubles their stake every time they lose. So then you'd have to modify here. So here we're just betting £1, but if you lose, it could be instead of betting a pound, next time you bet £2, and you're trying to sort of cover your losses. It's double or quits kind of argument. And then if you lose again, you can say, well, okay, I'm going to double the stake, double how much you can bet again, and then you'll get a different probability for A to win or B to win. And you can study all these methods using kind of the Monte Carlo method. And then you get a kind of probability of A to win or B to win. And you can vary the betting strategies. So that's one use of Monte Carlo to study sort of games. Okay, so there's been a very quick tour of Monte Carlo methods. The main application to Monte Carlo methods are to multidimensional integrals. Well, I think main's probably the one in mathematics. One good example is it's a very good way of computing high dimensional integrals, sort of beyond like four-dimensional integrals. But Monte Carlo methods are widely used modeling physical systems. We saw this example for percolation, and you can also do simulation of gambling. So it's a very powerful technique. It gets you usually gets you an answer, but sometimes it can be a bit inaccurate. So you have to spend time trying to improve the accuracy of the prediction.